Hi everyone, this is Dr. Delosier, and I'm going to be walking through the Spring 2024 EC312 12-week midterm practice exam, so you can hopefully learn a little more about how to attack these problems. So to get started, we're starting with question 1 here, which is a CAN messaging problem. And so we've got 4 CAN nodes connected to a bus, and we are to assume that the nodes are all sort of set up in the same way, where they've got 2 PWM outputs to 2 motors with different RPMs, and a set of digital output pins that are connected to a segment display that will be used to turn on parts of that segment. So answers are supposed to be given in the form node motor turns at node blank motor blank turns at blank RPMs, or node blank display lights up with decimal number blank. So we're going to be extracting that information from the CAN messages that are given, the data that's given. So to start, we've got a node consists of CAN message ID OX219 and 1 byte of data OXA0. So we're going to start by taking that OX219 and turning that into binary. You can do this with your calculators, and that's probably easiest and safest. I'll do it by hand here. So 0010 for 2, 0001 for 1, and 1001 for 9. We know that each CAN message starts with this leading 0, the SOF, and then a 4-byte message prefix, and that's going to be what we look up in the table, and then a 7-bit node ID. This is going to help us fill in some of that information that we're supposed to give. So we'll first look at the message prefix and check our table at the top of the page here and see what 0100 leads to. We should say that that lines up with RPDO1 here, right? RPDO1 is 0100, and that is a digital out D0 to D7. So that's what our data is going to be. And since it's digital out, we know that our digital out pins are connecting to this 7-segment display. So we can start our message of node blank display lights up with decimal number blank. So we still need to solve those couple blanks here. We'll figure out that next. So node ID is the first thing, right? If we can fill in that blank by just converting the node ID we've got here in binary to decimal. And so we've got 0011001 to decimal is going to be 1 plus 8 plus 16 is 25. So node 25 display is going to light up with a particular decimal number. That decimal number is going to be A0. And I'm just going to write up here OXA0 so that it lines up with our D0 to D7. So that's 1010, 0000. And we can see then for the 7-segment display, we've sort of got, or the single segment display, we've got our numbers connected to each line. And we know that 0 should be considered on here, and it's active low, so 0 causes the segment to light up. That's what we're told. So I'm just going to sort of fill in the lines that are listed as 0, and that's everything but 0 and 2. And you can see that D0 here is set to 0 permanently. D02 or DO2 is also off. So that looks like a decimal number 6, and we're done with that part of the problem. So on to the next one. We are looking at another CAN message and going to be interpreting that based on, again, the same information that we've got here. So let's do the same process, OX318 to binary, and that's going to be 0011, 0001, 1000, and then we've got our SOF, we've got our 4-bit message prefix, and then we've got our 7-bit node ID. So again, we'll look that up in the table and see that 0011 is going to be, 0110 for our message is an RPDO2, 0110, and that is a PWM out 0 to 3. So that's what our data is going to be, is our PWM out data, what we're going to set our motors to. And so then we've got our node ID. Well, let's write out our blanks first. So we're going to have node blank motor blank turns at blank RPM. And so that since this is a PWM message, we know that it's affecting the motors. We need our node ID, so let's again do 0011000 to decimal. And that's going to be 24 because it's 16 plus 8. So node 24's motor is going to be the one turning, or motors. Let's figure out what these are. So this is PWM 0, 1, 2, and 3. Those are the pins that are connected to the motors. And if we look down at our diagram, that means that pin 0 is set to 0. So we could also say, sort of the more complete message might be node 24 motor A turns at 0 RPM, right? Because it's set to not be on. And then our other pin 1, is connected to motor B. And so motor B is going to turn at some RPM. And we see that that actually has a value here, CC00. So important to note that OXCC00 is in little endian, right? So the little end of the number came first. So we need to turn that into OX00CC and then convert that to decimal. In decimal, 00CC is going to be 204. And so then from there, we're going to use the equation given on the sheet here, which is that all the PWM outputs, the conversion factor from decimal to PWM percentage is 100 divided by 255. So we're going to divide 204 by 255 and then multiply by 100. And that's going to give us that this is 80% of the total RPMs. Now we are given what that total RPMs is, which is here motor B is 2000 RPMs. So if we do 80% times 2000 RPMs is 1600 RPM. That's our final answer, 1600 RPM here. So it's a lot for the one question. That is how we would figure all those things out. The last part here, a node attempts to transmit a message from part A at exactly the same time as another node attempts to transmit the message from part B. Justify your answer and be specific about how you came to your conclusion. So I think what this is asking, there's no actual question here, is who gets to win, right? What happens when this occurs? So we've got our OX219 and our OX318, and we're going to translate both of those to binary. Same deal. So 0010, 0001, 1001, and then 0011, 0001, and 1000. And we know that the way that this works is that whoever is dominant on the bus is going to win, and 0 is dominant, 1 is recessive. So we read from left to right, matches, 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 and then the top message wins. So OX219 will win the bus arbitration, which means that node 20 or node 25's display will light up, right? So if this is what's supposed to happen based on the prior answers we gave, then its response to that will be what occurs. So the decimal number 6 will show on the display there. And the node 24 motor will not turn, right? Or it will not be able to be changed from what we did in the lab. I'm going to continue on to question 2 just because it also highlights CAN stuff, and it's right here. So sorry for the long segment here, but it's worth it, hopefully. So this says, suppose node 26 wants to send a CAN message reporting that its digital input values are as given. In the table below, fill in the first 27 bits of the CAN data frame it would generate. Don't add any stuff bits at this point. So here we're going back to our table of handy dandy CAN formats. And we are going to use the physical format over here, or the frame format is probably what I should call it, right? It's the physical format is the frame format with stuff bits. So we just read through this and we're going to put in the information as needed. So we start with the start of frame SOF bit, and so that is a 0. Right, that's our SOF. We're then going to give the message ID, which is the prefix for 4 bits, and the node ID for 7 bits. Right, so message prefix is going to come from the type of message that we're sending, and that is reporting its digital input values. So we'll look at the table over here and see that digital in is a TPDO0, which means that's going to be TPDO1 message. So that's going to be 0011 as our prefix. The node ID is node 26 is reporting its values, and so we're going to do 26 to binary is going to be 0011 for 24, 0, this is 10. So 7 bits to represent 26, and so we're going to fill that in here, 0011, 010. Look back down here to see what we say. 0 means data frame, 1 means remote frame. In this case, this is going to be a 0, so data frame. It says the next bits always 0 for our setup and always 0 for our setup. So those two are 0, 0 as well. And then from there, we have the DLC, which is the number of bytes of data. We are sending 8 bits. 8 bits is 1 byte. And so we are going to fill in our DLC 0001. Right, that's those 4 bits right there is our DLC. And then we have the actual data to transmit. So the data that we are supposed to send just gets filled into those 8 boxes to finish us up here. So we have 1, 1, 1, 1, 1, 1, 0, 0. And that's it for that part of the question. So the last part here is identify where any stuff bits should be inserted. And if we have 5 in a row, means stuff bit with opposite value. So that's what we're doing here. Let's look through our actual message. So no 5 in a row yet. Right here, we've got 1, 2, 3, 4, 5. So we're going to insert a stuff bit here. And then we switch back to 1s naturally. So 1, 2, 3, 4, 5. We're going to insert a stuff bit there. And then we don't have another 5 in a row after that. So we are going to say between bits 16 and 17, and between bits 23 and 24. And that's it for that whole CAN part of the test.